Hi, and welcome to the first in a series of videos on topics in thermodynamics. Today's topic is the ideal gas, which is a simple mathematical model of a gas, but is actually a pretty accurate approximation to real physical gases like the air in this room. The ideal gas model is useful not only because it's an accurate physical approximation, but because its simplicity makes it a very useful tool to keep in mind and use as an example when studying the laws of thermodynamics, which can sometimes get a little tricky. Today's video is focused mainly on the definition and some formal properties of the ideal gas, and the theme of the presentation is that if we use our knowledge of Newtonian mechanics and study the motions of the little molecules which make up the gas, and we analyze them carefully enough, then that alone is enough to tell us about the macroscopic properties of the gas as a whole. Okay, so enjoy. An ideal gas consists of a very large number of very small molecules moving around in some kind of container which don't interact with each other at all. This container has some volume, V, which we call the volume of the gas, and the bouncing molecules exert a pressure on the walls of the container, which is the pressure of the gas. The number of molecules is really very large, 10 to the 23 being a typical number. A fourth state variable called temperature tells you how hot the gas is. These four variables are what we use to describe the state of the gas, and the ideal gas law relates them. We can derive this law by carefully analyzing the gas contained in a cube of side length L. Consider a single molecule of the gas moving in the horizontal direction, which we'll call the x direction. When the molecule hits this wall on the right-hand side, it will bounce back and the x component of its velocity will be exactly reversed. We can compute the force that the wall exerted on the molecule to cause this change in velocity by first writing down the change in momentum of the molecule, which is 2mvx, m being the mass of the molecule. After hitting the wall, the molecule will bounce back and forth in the box and hit the wall again after time delta t equals 2L over Vx, and this will repeat indefinitely. The force that the wall exerts on the molecule averaged over many bounces is just delta p over delta t, or mvx squared over L, and this is equal in magnitude to the force exerted on the wall by the molecule. The pressure on the wall is equal to the total force from all of the molecules on the wall, which is the number of molecules times the average force per molecule, which I'm denoting by angle brackets F, divided by the area of the wall. The area of the wall is just L squared, and the average force per molecule is just the molecular mass m, which is the same for all the molecules, times the average of Vx squared, again denoted by angle brackets, divided by L. Multiplying these two factors together, we notice that the denominator is just L cubed, which is nothing but the volume of the box, and so we will replace L cubed by V for volume. This mv squared should remind you of kinetic energy. So let's write down the translational kinetic energy of a single molecule. That's the familiar formula 1/2 mv squared. Remember that v squared refers to the entire vector squared, so we'll write that as the individual components vx squared, vy squared, and vz squared. The ideal gas law, as we've derived it so far, involves an averaging over all the molecules. So let's take this average of the kinetic energy equation by including angled brackets around all the terms. Remember that the mass is the same for all the molecules, so we don't have to worry about average mass. Since on average we don't expect any difference between the x, y, or z directions, we can also write this formula as 3/2 times the average of Vx squared. We can solve this equation for the average Vx squared and write the ideal gas law as pressure times volume equals 2/3 times the number of molecules times the average translational kinetic energy. At this point, we're ready to introduce the last state variable, temperature, by taking this 2/3 average kinetic energy factor and just defining it to be some constant K times the temperature of the system. Thus we find the final formula of the ideal gas law, PV equals nKT. To summarize, we find these two important formulas for the ideal gas, PV equals nKT and average translational kinetic energy equals 3/2 kT. Sometimes the second one is written as total translational kinetic energy equals 3/2 nkt. K is called Boltzmann's constant, and by dimensional analysis we see it must have units of energy per temperature. And temperature in thermodynamics should always be measured in the absolute Kelvin scale. K is just a unit conversion factor, and only really exists because, historically speaking, temperature was around before people knew it measured some kind of energy, and so it was given its own special units. Now it's time for an example of how to use the ideal gas law. Consider a gas contained in a volume V with pressure P1 and temperature T1, and now put a candle under it to heat it up. When we do this, the temperature will increase from T1 to T2, but the volume V will stay fixed. Our objective is to find out what happens to the pressure. We start by writing down the ideal gas law, PV equals nkt, and then rearrange the formula such that everything that changes is on the left-hand side, and everything that stays the same is on the right-hand side. So P1 divided by T1 equals Nk over V. But Nk over V is constant, so this is the same as the final pressure P2 divided by the final temperature T2. Now it's just a matter of solving for the final pressure P2, and we find that P2 equals T2 over T1 times P1. All ideal gas law problems work in basically the same way. You write down the ideal gas law, then put everything that stays the same on one side of the equation, everything that changes on the other side of the equation, and then set things that stay the same equal to each other. One useful tool to keep track of the state of the system as it changes is the PV diagram. An equilibrium state is one in which all of the state variables are well defined and the ideal gas law holds. These are the states which can be plotted on the PV plane. Every point on the PV plane corresponds to a state with a particular pressure and volume. A horizontal line means changing the state at constant pressure. That's called an isobaric process. A vertical line means changing the state at constant volume, like the previous example, and that's called isovolumetric or isochoric. To keep the temperature constant means moving along the PV plane in a hyperbolic line. To see that a hyperbolic line indeed corresponds to constant temperature, we just have to use the ideal gas law, PV equals nkt. And when the temperature is constant, we see that the pressure is proportional to 1 over the volume, which of course is the equation for a hyperbola. There's one other topic that I'd like to introduce at this point, and that's the equipartition of energy, or equipartition theorem. The equipartition theorem is sort of a generalization of this formula which relates the kinetic energy of the molecules in the gas to the temperature of the gas. Remember that the kinetic energy of an individual molecule is 1/2 times the mass of the molecule times Vx squared plus Vy squared plus Vz squared. In a monatomic gas, where the molecules are really point-like objects which have velocity vectors v and no other internal structure, this represents the entire energy of the molecule. But a molecule could be more complicated. A diatomic molecule, which we can model as 2 tiny atoms connected by a rigid rod, can do more than just move around. If I draw this vertical axis here, we see that the molecule can rotate around that axis. Call it axis A. There's another axis coming out of the screen that the molecule can also rotate around. Call that axis B. The total energy of this molecule includes 2 additional terms. One for the rotational energy corresponding to rotation around axis A, and another for the rotational energy corresponding to rotation around axis B. In general, there's even more that a diatomic molecule can do. At very high temperatures, this bond between the atoms can start to vibrate. We would model this not as 2 atoms connected by a rigid rod, but as 2 atoms connected by a spring. And we have to include even more terms corresponding to vibration of that spring. There's one which is the kinetic energy of the vibration, which I'll call 1/2 mu squared, and another which is the potential energy of the spring as it vibrates, which is 1/2 kl squared. This k here is supposed to be the spring constant, not Boltzmann's constant. So the total energy of the molecule contains many terms, the number of which depends on the structure of the molecule. Monatomic gases contain 3 terms, diatomic contain 5, and diatomic at high temperatures contains 7. The number of terms in the total energy of a molecule is called the number of degrees of freedom, or number of quadratic degrees of freedom. The equipartition theorem says that on average, each degree of freedom of the molecules in the gas gets 1/2 kT of energy, and so the total internal energy of the gas, which accounts for all of the gas's possible motions, is equal to the number of degrees of freedom d divided by 2 times the number of molecules n times k times t. Okay, that was the ideal gas. And with that tool at our disposal, we are now ready to attack the laws of thermodynamics, which we will do next time. All right, see you then.